Hello, and welcome to part 3 of the National Weather Service Pittsburgh Spring 2023 Basic Spotter Training Program. As a reminder, if you're looking for additional online training, you can find those through Comet MetEd and the Spotter Network, which have online courses that are approved and recognized by the National Weather Service. These come at no cost to you and can further supplement a lot of the information that you'll learn through this basic training program. In this presentation and video, we'll be talking about the basics about thunderstorms, how they develop, the different kinds of thunderstorms, and really a lot of the background information to understand and successfully spot severe weather. So to get started, we're going to go over a lot of the basics about thunderstorms and how they form. There are 4 main ingredients that you need for the development of thunderstorms. You need wind shear, lift, instability, and moisture. With wind shear, this is in reference to the different wind speeds that may occur throughout the column of air, and this acts to help to better organize and create potential for rotation and tornadoes. Lift is an agent to help air particles start to move upwards through the atmosphere. The upward motion is what leads to eventually the creation of clouds and then thunderstorms. One agent of lift is unstable air, where basically air is colder as you go with height. Instability is another aspect, and this is where air is able to accelerate upward or downward once it started up or down. Instability is a measure of how quickly an air particle rises through the air, and this is again determined by the impact of temperature differences between the surface and the air aloft. Finally, any thunderstorm can't really develop without moisture. You need to have water content to actually have these clouds and different features form. Preferably, you'd like to have this moisture located in the lower to mid levels of the atmosphere. If it's located solely in the upper levels of the atmosphere, it becomes too high up to develop into any sort of storm. So the life cycle of a thunderstorm kind of comes in 3 basic phases. The first phase is a towering cumulus stage. Here, an updraft develops. You have moisture and lift creating rising motion thanks to unstable or unstable air. This rising motion is what creates the updraft. As that rising air moves upwards and condenses, it helps to form the basis of the cloud in that towering cumulus. Stage 2 is what we consider the mature stage, and at this point we have a fully formed thunderstorm. We have an updraft where air is being lifted, rising thanks to unstable air, and because enough hydrometeors have developed within the cloud, based on an ability for air to move downward, and just through something as simple as gravity, some of those air particles starts to fall, creating a downdraft. And through this downdraft, you can start to generate things like lightning and rain. For a typical different types of thunderstorms, these, based on the storm type, they can last in this mature stage for different ranges of time. We'll get into the single cell, multi-cell, and supercells, the different types of storms, in a little bit later, but just know that for the more intense storms, they can typically last longer in this mature stage. Also note at the very top of the storm is the anvil. What is happening here is that the warm rising air is eventually hitting air that is warmer than it, or basically as it cools, as it goes through the atmosphere, and it hits a level where the air finally is warmer. This causes it to trap, or kind of creates a lid on the rising motion. At that point, the air is forced to spread out. So this moisture is forced to spread out and creates this look of an anvil. The third stage is the dissipating stage. At this point, we've lost our updraft. Whether instability has gone away, our source of lift, whether it's a cold front or other lifting mechanism has gone away, has now caused the updraft to end. Without the updraft, we can't maintain it. So all that's left is just a downdraft. Eventually, the storm rains out, clouds are left over, and no more storm exists. There are 3 main types of thunderstorms, though there are kind of subsections potentially within each section. There's a single cell, multicellular, and supercell type of thunderstorm. For single cells, we typically associate these with kind of weaker wind shear environments. They're slowly rising up and generally kind of falling down. And little to, if any, severe weather typically develops with these single cell thunderstorms. They are short-lived, lasting between 14 or 15 to 45 minutes. Sometimes it can develop small hail up to maybe quarter size, about 1 inch. So it can have severe if they are able to rise and have hydrometers last long enough to accumulate for that hail. They can produce gusty winds and maybe a brief weak tornado. But again, these aren't our big severe weather makers. What happens is with a weak shear environment, the updraft develops on the right hand of that image there, and something like a cold front's causing that warm air to rise. The rain and the downdraft pulls all that rain down and eventually weakens out because the wind shear isn't able to maintain it maybe as well. In a multicellular thunderstorm, these end up being more of our common severe weather producers. They can last anywhere from 45 minutes to upwards of 8 hours. They have the capability of producing large hail, damaging wind, especially for a large area. Can't rule out brief to strong tornadoes and maybe even extensive flash flooding. Now, multicellular storms, maybe you've heard of them, but just maybe by different names. And there's a lot of different types of storm structures that fall within this category. Things like squall lines, which you can see this was a squall line in the previous image. You can also have quasi-linear convective systems, derechos, bow echo, mesoscale convective systems, or MCS, mesoscale convective complexes, or MCCs, mesoscale convective vortexes, MCVs, and we will test you on all those acronyms. Just kidding. Also, you can have things like line echo wave patterns. So all sorts of different types of multicell structures can fall within this, but they all seemingly have similar aspects and capabilities of producing severe weather. The last main type of thunderstorm is the supercell. This is kind of the one that I think everybody thinks of, your Oklahoma or high plains locations, and these are the big monsters, usually great photo opportunities, and these almost always produce severe weather. Sometimes they can be short-lived, but generally they're strong, long-lived storms that can last many hours and produce large hail. They're going to be the ones that typically are associated with the strongest tornadoes. They're not always strong, but typically associated with the strongest tornadoes, and can also produce brief flash flooding. But given their size, typically they're not the biggest of storms compared to a MCS or multicellular storm. They can produce a lot of heavy rain quickly, but hard to sustain it for a very long time over a given location. So kind of rehashing there the three different types. You have single cells, which are rarely severe, but are common. We kind of associate maybe with a typical summertime thunderstorm that doesn't have a whole lot of impact. Multicellular storms can occur often. A lot of times they're associated with cold fronts, and they often produce severe weather. Supercells are rare. It takes a lot of different ingredients for these for the environment to support a supercell thunderstorm. But if we do get those, almost always you can expect them to become severe. So there are different parts of a thunderstorm to actually understand and know what's going on. And the first part we're going to discuss is the updraft region. So thunderstorms need instability. And what kind of helps to create instability is by having warm, moist air near the ground and having cold, dry air aloft. As air rises, it cools, and some of that water vapor condenses, forming a tall cumulonimbus cloud. By having warm air near the surface and cold air aloft, that creates that instability because air will rise as warm air rises until it reaches colder air. The updraft can be found by looking for the rain-free base. So the idea is where air is rising, it's hard to have rain falling because you're not going to have anything falling down. So that's the area of the storm that we're going to focus on here over the next few slides to discuss the updraft and what we can see in the updraft region. So the one key aspect of being a spotter is being able to quickly, or at least eventually, finding that rain-free base. Finding the rain-free base really can help you orient yourself to where the updraft and downdrafts are within the storm structure. The rain-free base is where you can also watch for that tornado development, because a lot more often than not, tornado development occurs between the interaction of the updraft and the downdraft region. And we'll get to that a little bit later. Now, not all storms will have a clear rain-free base. A lot of this is idealized. And you can have times based on the environment where precipitation could actually obscure the base in what we consider high precipitation supercells, or even in some of the multicellular storms. But looking at this graphic and kind of structure here, if we're able to identify the precipitation-free base, we can identify where the updraft is, eventually leading to the cumulus-nimbus cloud and the overshooting top that it can occur when that warm air is rising so quickly that it's able to puncture the kind of that lid I mentioned a little bit before. You can also then define where the precipitation is falling, and that's your downdraft region. And in between those two regions, your updraft precipitation-free base and your precipitation downdraft area is where you're most likely to find your wall cloud and eventually tornado generation. And as we can see here, that's where it's highlighted, right in between those two features. You have your updraft rising up, downdraft falling down, creating precipitation, and in between is where you potentially can have your wall cloud and tornado formation. Here's now an example of that with a real-life photo. Here's a thunderstorm photo that was taken by Roger Hill back in May of 2010 in southeast Colorado. In this image here, we can find that rain-free base. Through that, we can identify that just to the left of that will be the updraft, and we can see where the precipitation is, and that's where the downdraft is. And it's in that area, that yellow arrow area, that we potentially could have tornado formation. So what are part of the features that we can see in an updraft? I've kind of mentioned it already, but one of them is a wall cloud. A wall cloud is an isolated lowering of the cloud deck. The key though, and we'll talk more about the different aspects of the wall clouds or clouds you could see, is that it has persistent rotation. That's because due to the movement of air and the different changes of temperature, you're going to eventually have this area of upward moving air to also be rotating in a counterclockwise motion. Typically, sometimes it could be clockwise, but in a counterclockwise motion. And that persistent rotation is the key aspect that defines it being a wall cloud. It often is kind of the precursor to developing a funnel cloud and eventually tornado. And we'll just talk about the differences with that soon. You will always find the wall cloud underneath the rain-free base. And as you can see in this image, the rain-free base and your updraft is where you're going to find the wall cloud, and it's going to be near where your heavy rain is, but in that rain-free area. So here's an actual photo from a storm that was taken, and you have an updraft region, and hanging below that lower cloud is the wall cloud. Now, sometimes it's really difficult just with a static image to know for sure that this is a wall cloud, and we'll discuss this more later. But when you're spotting out there and you're out in public seeing this, you'll want to use those visual clues and that persistent rotation to confirm that is a rotating wall cloud. And that's important information when you're spotting and reporting that information to the National Weather Service Pittsburgh office or another office, is to note that it has a persistent rotation. If it doesn't, it could be other features that you're seeing. And especially if you send in photos of these things, note these aspects, because just on the photo alone, it may be hard to tell. So again, what you're looking for is that rain-free base, and underneath it is a lowering cloud deck, that is the wall cloud. After you have the development of the wall cloud, now you're potentially setting up or having the precursor for a funnel cloud to develop. Now, funnel clouds are a rotating condensation funnel extending from the base of a thunderstorm. Now, funnel clouds may be sometimes described as tornadoes. Funnel clouds are not tornadoes. You can kind of say that it's a tornado in the cloud, but that we don't want to use that sort of terminology. What funnel clouds are is just, again, rotating funnel that extends from that base or from that wall cloud coming towards the ground. Funnel clouds are not something that is in contact with the ground, okay? Funnel clouds do not make contact with the ground. If they do, at that point, you have a tornado. Here are some pictures to also show that, some of these, what a funnel cloud may look like. It's kind of this rotating condensation funnel that is spinning up through the cloud, maybe extending from a wall cloud, and it's not making contact with any sort of ground surface. A tornado is now having that funnel cloud reaching the ground. It's a violently rotating column of air in contact with the ground. You can see a couple images here of examples of actual tornadoes that occur. Now, this is again something where it's extending from the wall cloud down to the ground and impacting the ground. Now, sometimes it can be very hard to know, even from a distance, especially at night, if there is a funnel cloud, wall cloud, or even tornado. Here was a picture taken from the New Kensington area of an actual tornado. What you kind of have to utilize during nighttime hours is things like lightning bolts to give you maybe enough light to see. And even then, it may be hard to tell if you have consistent rotation, if that object is hitting the ground, or things like that. So you have to be careful and try to note these things if you're reporting to a National Weather Service office, to try to look for and visualize, is there rotation that you can see between the different flashes of lightning? Is this in the right part of the storm? Is it where there's kind of the rain-free base? Things of that nature. Taking a little setback or sidetrack, we want to talk about just kind of understanding the climatology of tornadoes, so that way you can understand how likely and how frequent maybe they occur and how severity they occur in the National Weather Service Pittsburgh area. A vast majority of our tornadoes are of the EF0 to EF1 category, which generally means wind speeds between 65 and 110 miles per hour, serving as 75% of our tornadoes. Typically, these types of tornadoes are very short-lived, maybe associated with a multicellular system. They develop quickly and occasionally can happen without warning, because there's, especially with multicellular systems, it can be a quick spin up, creating quick damage before they lose the structure and environmental nature that allowed them to form in the first place. With EF2 and EF3 tornadoes, typically they are short-lived, but they are maybe longer-lived than the EF0 or EF1s. They can have wind speeds between 111 and 165 miles per hour and represent about 23% of the tornadoes that we've seen in the National Weather Service Pittsburgh area. They still can develop quickly without warning, but typically there may be a few more signs or indicators that we have as meteorologists to identify them quickly and provide that warning that maybe EF0 or EF1 tornadoes do not. The big ones, the EF4 and EF5, have very rarely occurred within our area. Doesn't mean they can't. It doesn't mean we in the future can't see them, but only 2% of them have occurred where we have wind speeds of 160 miles per hour or greater. These are typically long track tornadoes and are typically associated with well-organized supercells. So when you are out spotting and you see these sort of features, we want to know specifically these three things when you're reporting those about a tornado. We want reports of rotating wall clouds, reports of funnel clouds, and reports of tornadoes, because some of these can be the precursors to the actual tornado development. Getting that information to a Weather Service office quickly can help us maybe get that warning out a few minutes earlier, and just by getting a warning out a few minutes earlier can help to save lives and property. Key is also, if you're able to, provide picture or video evidence and report exactly what you see, and think of the ways you can describe it. Describe that lowering wall cloud and the lowered cloud deck. Is it persistently rotating? Is it in the rain-free base aspect of the storm? Do you see the funnel cloud in a consistent rotation? And are you able to tell whether that tornado is touching the ground or not? So again, let's take this look at this photo here from Fort Allen, Pennsylvania, along Route 30. That was taken on March 23rd of 2011. This clearly looks potentially like a tornado, right? Well, it's hard to say. Is it actually a funnel cloud that's just not touching the ground, or is it an actual tornado? So make sure that even if you're unsure, to kind of give that description and part of the process. Now remember, if you're spotting these aspects and these sort of severe weather, especially tornadoes, your safety is more important than tornado report. We have additional tools and ways that we can try to warn for these sort of storms and these sort of threats. If you feel in danger, you should take cover first before trying to report to us. Once you are in a safe location or you feel safe, that is the time in which you can pass that tornado report along to our office. Moving on, we're going to talk about the next part of a thunderstorm structure, which is the downdraft. And there are a lot more potential damaging hazardous things that occur within a downdraft, including lightning, heavy rain, hail, and damaging winds. So the first feature that we'll discuss is the rain-hail shaft. So no real trick here. The dark, ominous area where the precipitation is falling is called the rain shaft or the hail shaft. Obviously, it's also called a hail shaft at times if it's actually producing hail. Now, the color will vary depending on the lighting and your location relative to the storm. And some of this is based on how the sunlight may be hitting this region, if there's presence of hailstones that could reflect the light. But just know that typically your darker region is where you're going to find the rain hail shaft. Here's a few picture examples of what that maybe looks like. Not too often do we unfortunately see actual images of this in the at least the western Pennsylvania to northern West Virginia locations, because our viewing limits isn't as clear or as long distance maybe as you would see out in the greater plains like this. But still, you can see the feature of maybe where the rain-free base is, as well as then in these pictures, the darker, ominous looking thing falling to the ground being the rain hail shaft. And those are highlighted right there. Now, a rain hail shaft can form, but it doesn't mean it has to be severe. You can have plenty of rain shafts where hail's falling, but because of melting processes, it actually doesn't even become hail or reach the ground as hail and creates little impact. Sometimes the hail melts enough that it's maybe only the size of a pea, and in which case it's not severe. So just kind of know the differences, that maybe you see a rain hail shaft. That's not necessarily in on itself something to report. Now, if you're crossing an area where that's been impacted by say a hail shaft, and you see hailstones that are on the ground that are a nickel or penny or greater size and diameter, that's the time to potentially report that to a National Weather Service Pittsburgh office. Speaking of hail, this is one of the downdraft hazards. So what happens? Well, moist air is lifted through the updraft. We've discussed this. This provides kind of the moisture that is the fuel, if you will, for a storm. Those water droplets, as they go higher up in the atmosphere, eventually freeze, because the freezing level, our temperatures at that height eventually are below freezing. Even though the water droplets may go above or into, say, below 32 degrees, it may still take some further upward lift to get it to fully develop into ice. What happens then is that because this updraft is continuing to bring in new moisture, what happens is these ice and these waters continue to interact as they kind of bounce up and around through these convective currents. Like they try to fall down, but then the updraft lifts them back up. Then they try to fall again, they're up, then they bounce back up again because the updraft is strong enough to keep them floating up above. This interaction creates the ability for water to kind of come in contact with developing hail, and eventually that water accretes onto these ice stones and makes them bigger and bigger. Eventually, when the hail becomes too big or where the gravity of trying to pull it down, and the downdraft trying to pull it down is too great for the updraft to keep it up, it'll fall down as a hailstone. As you can see, you can kind of see the three-part process of the warm air rises, the droplets freeze together as it interacts with the freezing layer, and the hailstones eventually falling down because they become too heavy for the updraft to support. So what do we do when we see hail? How do we report hail? Well, as spotters, we do like to hear reports of any size, but the key threshold we kind of use is dime or penny size. At this point, that's when we need to issue or be alert to what is coming out of a storm, because that'll dictate or really guide our severe weather operations going forward. Now, if you can't measure, try to use a common object to compare this hailstone size. Ideally, you would take out a ruler and measure the actual hailstone to see what its diameter. But you can use common objects, and we have this handy guide here. Now, when you're reporting hail, before we get into the different sizes, we want to know what the largest hailstone is. This, to us, shows us the maximum potential hailstone that could come out of a storm, and that did come out of a storm for a potential area. And include details when you're reporting. Here's the largest hailstone size, but it was only like 1 or 2 stones that were this size. The rest were X size. This little few details really helps to better describe what you're seeing there on the ground to help us better make those decisions. From here, from this graph, you can kind of see the sizes that you can kind of compare it to. dimes, nickels, quarters, eventually things like ping pong size balls, golf balls, some sort of object that's a uniform shape. One thing we do not want you to compare it to is things like marbles. Marbles or other objects sometimes can come in different sizes. Some marbles may be bigger than other marbles. Bouncy balls may come in different sizes. That doesn't help us because we don't know if you're talking big or small or what it is. Just try to use this nomenclature of different coins or then different ball objects that have a uniform size no matter what they are. Things like baseballs, tennis balls. And that really helps guide us on what you're seeing there on the ground. As I mentioned, do not compare it to marbles because not all marbles are alike in size. Another potential hazard within the downdraft region is heavy rain and flooding. Obviously, rain is going to come down in the downdraft, and if that water, if there's a lot of moisture being fed into a storm, eventually it falls out. There could be a lot of rain that falls out of it. Thunderstorms are notorious for potentially creating a lot of locally heavy rain in a short amount of time. Think upwards of 3 to 5 inches in less than 3 hours. This can be very problematic for any area, let alone urban areas where there's less grass or areas to absorb and take in that water, and it quickly floods. Another potential impact that storms can have and storm environments can have is not only could they produce a lot of heavy rain in a short period, but if the right environment exists, they could have multiple thunderstorms go over the same area, or as we say, train, because a train has multiple cars going over the same track. We could have thunderstorms train going over the same location over a long period of time. If this occurs, what happens is all this water falls in a quick amount of time. It can't run off into the proper storm drainage, so you can see things like washed out roads and bridges. It can force evacuations in flood-prone areas or flood getting into homes. You can cause structural damage, and it's very, very dangerous. Now, a key thing to remember is that if you see flooding, report that to us and kind of describe the depth of it, where that location is at. But also, if you are out and it's potentially flooding, do not try to drive through flooded waters because you don't know what's happened to that roadway or surface underneath it. Sometimes roadways can be washed out and you wouldn't know it, and it makes it more likely for you to be washed away in your car. So reporting flash flooding. We do want reports of any kind of unusual flooding, especially if it's water that is moving quickly. Now, there can be times where we get a lot of heavy rain and water's flooding over there or moving all over the place and the road looks flooded. But you have to also try to, as best as you can, think, do we typically see this sort of flooding in that area or not? There are some locations, especially in urban areas and especially in places like Pittsburgh, that when it rains and it rains heavy, this street floods. And it's just a problem of design, area, terrain that causes it to flood, even if it's not necessarily impactful or serious flooding that threatens life and property. So try to keep that in mind. But in general, report any sort of unusual flooding you see, and don't assume that we know about the flooding, especially even if there is a road closure sign up. We try to get through as many reports as we can. We try to have a lot of agencies report stuff to us, but there's only so many people who can remember sometimes to report this information to us. So always report this sort of information to us so we can ensure the proper hazard products are out for it, especially during the overnight hours when a lot of our agencies, our core partners, aren't able to provide that information to us. But we'd also definitely recommend, especially in the overnight hours, to not go flood chasing. For an event where flash flooding is possible, we're issuing a lot of stuff, don't go out looking for it. If you see it by chance, report it to us, but don't go looking for it because you put yourself more at risk. Now, keep in mind, it doesn't take much water to cause a lot of issues. All it takes is about 6 inches of fast-moving water to knock over and carry away an adult that's standing there, 12 inches to move away a small car, and 18 to 24 inches of fast-moving water to move most large SUVs, vans, and trucks. So it doesn't take much water on roadways that are especially fast-moving to cause flooding issues. Another potential impact in a downdraft location is lightning. While this is not formally a severe weather threat, and it's not going to be something that the National Weather Service will issue a severe thunderstorm warning about, it is still something to be aware of and try to mitigate your risk by trying to get yourself indoors. What happens is, as you have the updraft bringing in water molecules, and they're rising up through the atmosphere, these molecules eventually turn into ice. Ice eventually, because there's an interaction between the updraft and downdraft, collide with one another. These collisions end up making different charges and different charge structure throughout the cloud or throughout the storm, where you end up having positive charges developing in the upper regions of the thunderstorm towards the anvil. The center of the storm is typically a negative charge, and you start to have a small positive charge at the bottom of the storm in the rain, kind of the updraft's initiation, downdraft ending area, with positive negative charges forming on the ground. As you have all this positive negative charges forming, eventually if the charge interaction or intensity between these charges gets strong enough, you'll eventually have a lightning bolt that forms and moves from one to another. You can have cloud to air, cloud to cloud, within the cloud, or cloud to cloud types of lightning. Now, while they may not be a severe weather, you still have to know how to respond to it. If you're close enough to hear thunder, you're close enough to be struck by lightning. As you can see from the previous image, even if you're not in a location where there's a rainfall, there's many times where you can have a lightning strike that hits you outside of the rain. So if you're close enough to be able to hear thunder, you're close enough to be struck by lightning. It's safe to use a 30-minute period time after a storm passes to resume outdoor activities to ensure you're not within the range or threat of being struck by lightning. And always, it's a great message to pass along to other friends or family that you know, that when you let me try that phrase again. When thunder roars, go indoors. Try to stop all activities and seek shelter in a building or higher top vehicle to ensure you're not at risk of becoming a lightning impacted person. Another downdraft hazard is called damaging winds. What happens is with the rain, hail, cooled air that's falling down and through the downdraft, it becomes denser than the environment. This denser, heavier air falls out of the thunderstorm with winds spreading out in all directions. The difference between the density of air is what helps to dictate how fast that wind is moving out in all directions. Sometimes these winds can be sporadic, as maybe people have heard, especially in the Pittsburgh area, of microburst, or they can be sustained, like a squall line or a derecho, depending on the evolution and the type of storm that's producing this downdraft wind. What happens, what you'll see in this graphic is that you have warm inflow air, that's part of your updraft, eventually interacts with a gust front of this rain-cooled air spreading out where you can create roll clouds. And the density differences between these features helps to create the strength of those winds. So one of them is called microbursts. And there's a nice little video that was able to capture one of these microbursts happening. One way a microburst can happen is that during the storm's mature stage, you have a rapid distension of rain-cooled air falling through the cloud. This rapid distension hits the ground and spreads out in a kind of all directions fashion that can lead to dramatic localized damage. With these sort of microbursts, you can have wind speeds that it can exceed 80 miles per hour. So that's EF0, EF1 type of damage just from a downburst of wind. It can be very dangerous. As this rain-cooled air is kind of sucked into the middle portion of a mature storm, it's forced down and accelerated downward, and it creates that strong damaging microburst wind. These types of storms and these types of microbursts can be very difficult to identify on radar, and sometimes occur with short warning periods, and can be difficult to think. So if you do see damages from these types of winds, it's good to report that to us as quickly as possible. Here's some examples of damages that are caused by outflow winds. What is a key thing to understand with damaging winds versus a tornado is that outflow winds, straight line winds, microbursts, all typically have impacts where trees or damages are all blown in one direction. If you see it all blown in one direction, that you can surmise that most likely it was a damaging wind, straight line wind type of scenario. For something like tornadoes, damage will maybe be strewn in multiple different directions, or maybe in a swirling type of pattern, which coincides with the swirling, rotating nature of a tornado column of air. Typically with thunderstorm damaging winds, they are more widespread than tornadoes. Tornadoes are pretty localized in nature, very small, whereas damaging winds can be associated with a larger line and cause a longer path of damage and wider path of damage. And don't be fooled though, just because it's not a tornado, that it is not a threat to the public. Damaging winds have been measured to be as equal to EF2, EF3 tornadoes. So they can be just as extreme, if not more extreme sometimes, than tornadoes. Here's an example of one event that comes from a damaging wind derecho event. Derechos are a type of multicellular storm that form and can travel great distances, great miles, and create widespread impacts. This was a derecho from the June 29th, 2012 event that developed first across Iowa and spread across Illinois, Indiana, Ohio, and into much of the Mid-Atlantic region. As you can see by the SPC storm report graphic, there was over 800 wind reports and 57 hail reports out of this system, causing widespread damages, power outages, highlighted by the image to the bottom left of Iowa, where there's widespread power outages from this derecho. So how do we report wind damage? Well, report the wind damage details, such as tree damage. How big was the tree? How alive or healthy was the tree? What was the size of the branch that was damaged or snapped off? Report any sort of details about the building damages. Was it shingles blown off, siding blown off? If there were any known injuries that occurred because of the damage from winds or things being blown around. Just like anything with hail or even tornadoes, pictures and video are always more helpful, because that helps us to visualize and collaborate some of the report that you're providing to us. If you're not sure if it was a tornado, just report it as wind damage. What we'll do on our side is review this storm damage and collaborate it with radar images and environmental analysis to help to determine whether maybe it was a tornado. And if there's a potential it was a tornado, we will then send out a storm survey team to assess the situation further to make that assertion whether it's a tornado required. I think that's a key thing to take away from this aspect of wind damage reporting. It's probably safer to assume that maybe damages was from wind unless you actually saw the tornado yourself and can report that to us. If you have any uncertainty whether it was a tornado or not, don't advertise it as a tornado. You advertise it as wind damage because, as we've discussed, wind damages can be just as intense as tornadoes, and we'll take the time to ascertain later whether it was a tornado or not. Another feature of the downdraft is the shelf cloud. Now, this is a thing that can look very ominous and looks kind of maybe scary at times. And it's a very common photo and visual to see with any sort of storm moving into an area. But it does not mean a storm is severe. What happens is that you have rising motion, again, your updraft, your warm inflow air moving along the gust front. This gust front may be your rain-cooled air that's spreading out, creating gusty winds. This interaction between this updraft and this flowing out cold air is that you have a temperature difference between these two that causes a natural wanting to create a spin or rolling type cloud. And we'll talk about the different features and looks this has here in the next couple of slides. A shelf cloud is one of these features that you maybe see, and is the most common type of storm photo that you'll visualize. And it looks like an alien space saucer just rolling through the plains or any given location. Again, if you see a storm that looks like this, it does not mean a storm is severe. Doesn't mean a storm isn't severe, and you'll have to use our other indicators to help us ascertain whether that threat is, but it on itself can happen with just even a non-severe thunderstorm. As you can see from the bottom right, you can kind of visualize it a little bit. You have rising motion along the gust front, this cold, gusty air moving out from the downdraft, and warm air rising up over it, leading to an edge of the downdraft's rain-cooled air, creating kind of a shelf look thing. We love these shelf cloud pictures. You can always send it to us, but it's not something that you necessarily need to call into our office or create a specific storm report for. Similar to a shelf cloud, a roll cloud is basically a feature that the rising motion air is further detached from the surface as cold air is rushing out from a downdraft. So rising motion is occurring along the gust front. The leading edge of the downdraft's rain-cooled air is zooming out ahead of the storm, and there becomes a disconnect, creating where there's more interaction between this rising warm air and outgoing cold air, creating a circular motion that creates a roll. If the cloud becomes detached from the parent storm, it is called a roll cloud. Again, we love pictures of shelf clouds. We love pictures of roll clouds. Definitely send it to us. It's fun, it's fascinating, it's great to share, but it's not necessarily something you need to report to us or call in or describe as something that is severe. So kind of again, what we want to note here, harkening back to the tornado aspect, is that there's differences between a shelf cloud and a wall cloud because they also lend to different potential weather hazards. A shelf cloud suggests that you're seeing a downdraft and an outflow. The downdraft has created this cold air, and that outflow from that storm is creating a gusty wind, creating a shelf cloud because of the interaction between that and the updraft air. It typically isn't moving away from the precipitation area. So if you see this cloud that's kind of trending or looks like it's reaching out away from the area of precipitation, that's probably your shelf cloud. It slopes downward and away from precipitation, and generally is not necessarily associated with severe weather. If it is, it's probably just a brief period of gusty wind. Whereas a wall cloud, which again is maybe a precursor to a tornado, suggests updraft and inflow, because that's where your rising air is interacting with the downdraft. And it's able to maintain its position with respect to the precipitation area. So it's near, but not within, but it's still within that rain-free base. And it slopes, typically wall clouds slope upward and away from the precipitation. So not downward, but upward. That upward motion is again indicative of the updraft and is a healthy sign that it could be a precursor to a tornado. So understand, try to these little subtle differences, but when it comes to spotting and reporting information, these subtle differences can be the key between potential action that a weather service meteorologist takes and does not take in a severe weather event. So one other thing to kind of keep in mind when you're looking at updrafts and downdrafts features is something called Scud clouds. These are very common, and it's okay to mistake these. These are difficult to ascertain what's going on. Scud clouds are kind of these low, ragged, and wind-torn cloud fragments that are usually not attached to the thunderstorm base. They can look like they're attached, or it can be hard to tell, but they're just these low clouds looking ominous. They typically are going to be moving away from the rain base, and they do not rotate, and that's the key part here. While it maybe looks like something that's reaching out, could be a tornado, or maybe just, in this case with this picture, a funnel cloud, the key part is standing there and visually continue to watching it to look to if it's rotating. If it's not rotating, and typically our Scud clouds do not rotate, that's a sign that you are not seeing a funnel cloud. And so the threat maybe for a tornado is not as imminent as you would maybe anticipate. They can look scary and they can look weird or kind of just uncertain of what they may produce, but just know that they're not scary, and it's very common with storms and not necessarily a precursor to any sort of additional weather hazard. Here's another photo of what we would consider a Scud cloud. Now on first glance, again, could this be a funnel cloud? You maybe have a little bit of you're in your rain-free base area, so you're in an ideal area. You can maybe say that's a wall cloud there with a lowering funnel cloud, and that potentially could be dangerous. However, if you took more time to kind of review the photo or specifically watch it in real life, what you're looking is for that rotation and consistent movement towards the rain-free base. And if you don't have that, then you can alert the National Weather Service that, hey, I'm seeing things, but it's likely it's Scud clouds because it's not doing these things. And that is good information to pass along rather than assuming that it's a wall cloud, funnel cloud tornado. So a quick review here. There's all sorts of different kind of regions and things to kind of look for when we're spotting and trying to dissect a summertime thunderstorm. What we want to first focus on is the rain-free base area where we'll find our updraft. That's located here. In this rain-free base area is typically where we can have our wall cloud develop and eventually maybe a tornado. And it's where we have all this rising, warm, moist air becoming the inflow into the storm, helping to generate and provide the fuel, if you will, for the storm, creating the updraft. As mentioned here, within the updraft, because of things like wind shear or different speeds of wind, it helps to cause the air to rotate throughout the column, which helps to either strengthen or intensify a storm and creating better potential for eventually hail and other factors. Next, you want to identify the downdraft. That's the area where you're going to have your rain base. All the air motion is now coming down, and with it, hydrometeors or water is coming down, maybe some hail. You can have your heavy hail. All these things can help eventually kind of help you diagnose that. A gust front coming out of the downdraft is then a sign that cold air is racing out ahead of the actual storm base. It can create a gusty wind and create different things like shelf clouds or roll clouds. So as a review of our different hazards from thunderstorms, frequency, and what to kind of do, hail is a very common thing to see, but when you get to higher hail sizes and potentially severe hail sizes, it becomes a little bit less common. Should you report that to the National Weather Service? Yes, especially if it's pennier size or larger. What you should also keep in mind from a safety perspective is that you want to try to head indoors and stay away from windows, especially with larger hailstones that could break glass objects. Another hazard is lightning, and it is frequent because a thunderstorm by definition has lightning. Is it something to report to the National Weather Service? No. Unfortunately, it's not something we issue warnings on, but it can still be impactful. It's just because of how frequent it occurs, people are just are meant to taught and understand the threats it has. What you can at least report the Weather Service in that instance is if there's ever any injury or major damage caused by lightning. And remember, when thunder roars, head indoors for your safety. Flash flooding is also a common thing, especially across the eastern Ohio, western Pennsylvania, and northern West Virginia area. It can happen all times of day, and especially you want to report it if it's unusual. It's not flooding that you typically see in an area. So remember, if you're out seeing it, report that to us, but also make sure you're not part of the problem. So turn around and don't drown. Never cross a flooded roadway. Damaging winds are a common aspect of a thunderstorm as well. So you do want to report that to us, especially if damage occurs. Now, sometimes people want to try to report to us that there was wind gust and they didn't see any damage, but they want to estimate at a certain speed. May want to extend it way for that, because I think many times we overestimate or inflate wind speeds based on how gusty it was. So kind of focus on damaging winds when it has damage occurring and what sort of damage occurred. So if you do see that, also keep in mind to stay indoors and stay away from windows in that scenario. Tornadoes are more rare, but that doesn't mean they still can occur across our forecast region. So of course, you definitely want to report that, and but also remember to not assume that wind damage is a tornado. Let that determination be decided by our office. Stick to the facts, stick to what you do know and what damages you are, giving detailed information, and we'll help to collaborate whether that was a tornado or not. And remember, if there is a tornado, you see a tornado, to make sure to go inside a sturdy building to the lowest level or interior room to keep yourself safe. Well, this concludes our video number 3 of our 4-part series of the Spring 2023 Basic Spotter Training. You can check out our other videos in the links below. Otherwise, have a great day.